Okay, good morning and welcome to the third week of the 2021 QMC workshop being put on by the Center for Predictive Simulation of Functional Materials and graciously supported by the U.S. Department of Energy. My name is Jaron Krogel. I'm from Oak Ridge National Laboratory, and I will be speaking today about statistical analysis and how to perform quantum Monte Carlo workflows with the Nexus tool. As a reminder, the workshop materials and today's slides can be found on GitHub at the link below. And these links, as well as others, will be reposted in the Slack channel. To give an outline of what I'll be talking about today, I'll first talk through examples of statistical analysis of quantum Monte Carlo time series data, which will be needed to analyze the results of QMC simulations. Next, I'll give an overview of the Nexus QMC workflow automation system, which we'll be using in the labs and which can be used for production quantum Monte Carlo calculations and has been used in many publications to date. Next, I'll give an overview of the week 3 lab material, which includes running variational Monte Carlo, performing Jastrow optimization, and diffusion Monte Carlo with QMCPAC. Since we have labs today, I probably will not take up the entire 2-hour block with speaking material, but please use the remainder of the time to work through the labs. Also, please tune in next week for molecular QMC calculations that will be presented in more detail by Anwar Benali from Argonne National Lab. There you'll be looking at single multi-reference wave functions for molecules in the virtual machine. Okay, for our first topic today, the statistical analysis of QMC time series data. There are several topics relevant to statistical analysis, but the most foundational are Gaussian distributions, and understanding them is essential to the analysis of all QMC data. The Gaussian distribution, as you likely know, has this form. It's an exponential of a parabola with a mean x bar and a width sigma. I denote the distribution p of x. To obtain the mean or the expected value, I'll use this angle brackets notation to denote the mean. That represents this integral over the distribution with x. And for the Gaussian distribution, if you perform that integral, you get back x bar, which is the mean or center of the distribution. The variance is related to the distribution width. It's denoted sigma squared and is computed by this combination of expectation values, the expectation value of x squared minus the mean squared. Within an integral notation, it looks like this. And for the Gaussian, you get back sigma squared. The mean and variance can be estimated from simulation data in the following way. If you have a set of samples xi drawn from the distribution p, say you have m samples, the mean is computed this way, the sum over x divided by the number of samples. And for the variance, the estimate is similar. It represents these, similar to these integrals above, where you subtract the mean, expectation value of the squared values, and this gets you the variance of the distribution. Specifically, I'd like to note that this is for m independent statistical samples that will become important later. But before we move on, let me emphasize some statistical reasoning, which will be generally useful for everything that follows. And this comes from the percentiles of the Gaussian distribution, which represents statistical significance. So if you have samples xi drawn from the distribution p, they will follow this distribution, the bell curve or normal distribution, where these vertical lines are marked at 1 sigma, 2 sigma, and 3 sigma lengths, where sigma is the standard deviation, again, the square root of the variance. And one important thing to note is that if you take a particular observation from the distribution that you have in hand, 1/3, so about 31.8%, or about 1/3 of the observations that you'll see will fall about 1 sigma away and beyond from the true mean. Additionally, about 4.6%, or 1 in 20 observations, will fall greater than 2 sigma away from the true mean. And for 3 sigma and beyond, it's more like under 1%. This type of reasoning will be essential as we consider the statistical error bar. To get to what I mean by the error bar of the mean, it's important to introduce the central limit theorem. The central limit theorem is essentially that the distribution of estimated mean values follows a Gaussian distribution. And so to get there, we'll start with a Gaussian random variable. I'll denote that eta, that's just sampled from a distribution n, which is the unit Gaussian distribution. You should think of Gaussian random variables as being sampled from the distribution in a sequence, just like you'd obtain from a simulation, where in aggregate, the whole collection of them represents the distribution. But for pure random variables, there might be an infinite number in the sequence. Here, the expectation value of eta, again, is 0, because the distribution centered at 0, and its variance is 1. If you take a collection of Gaussian random variables, eta I, and sum them, say you sum m of them, you will just get back another Gaussian random variable, another Gaussian distribution, but with a larger width. The standard deviation will grow like the square root of m. Okay, and that's generally true. All right, now for the magic of the central limit theorem. Let's look at arbitrary random variables, say a set of random variables denoted xi, drawn from an arbitrary distribution p of x, where the mean of each xi is some x bar, the mean of p of x, and the variance of each xi is just some sigma of x squared, which is the variance of that distribution. It's almost arbitrary within these two constraints, that the mean and the variance are well defined, that they are finite values. But beyond that, distribution can be arbitrary. And the central limit theorem relates to sums of these arbitrary random variables, where if I take m of these xi random variables and sum them together, what you get back is, again, another random variable, but that obeys a Gaussian distribution eta, where the distribution has a standard deviation that grows like the square root of m times the original standard deviation, and it's at a mean, which is just m times x bar. That is the central limit theorem, and we can apply that to the mean. And again, the magic of it is that you can start with samples drawn from an arbitrary distribution, but in the end, the sum of them obeys a Gaussian distribution, and thus you can use Gaussian statistical analysis from there. Okay, so what's it look like if you apply the central limit theorem to the mean? So we represent the mean again, expectation value of x, as this integral over p times x. And if you represent that as a finite sum of m random variables, remember these are random variables drawn from the distribution p, and you divide by m to get the mean. The sum is just as we said over here. It's this new Gaussian random variable, and then you divide through by m. And as expected, the mean is just x bar, but it's important to note that it's now dressed as a statistical distribution, eta. There's an uncertainty in the mean, which is related to the standard deviation of the original distribution, but now divided by the square root of m. So the more samples we have, the more precise your estimate of the mean becomes. And I illustrate that on the right. Here in black is the distribution, say p of x, and below, as these kind of shorter lines, I represent the successive distributions of the mean. So if you were to sample the mean from this formula, and you only use 10 samples, you can get mean estimates that follow this red distribution. It's pretty wide, right? You have a large uncertainty in the estimates. Whereas if you took m equals 100 samples or m equals 1,000 samples, the distribution of the means that you would get narrows. And so your certainty in the mean increases, but at a large expense. You need 100 times more samples to shrink this width of the distribution of the means by 10. Okay, this width of the distribution of the means is called the error bar. So this is the standard deviation of the distribution of the mean. The error bar sigma e is just sigma x divided by square root m. And I'll stress that this is for statistically independent samples. We'll consider the case of correlated samples in a minute. But first, I would like to visit QMC energy distributions and some applications of the central limit theorem to them. So the first thing I'd like to emphasize about quantum Monte Carlo energy distributions is that they obey variational and zero variance principles. And the application here is that you can judge the quality of different candidate solutions or different wave functions. So the expectation value of the energy in QMC can be considered an integral in energy over a probability distribution of energies times E. But in reality, you obtain the energy distribution in a specific way. And that is, instead of integrating over energies, you integrate over electron positions. And there are n electrons in a three-dimensional space. And so you're performing a 3n dimensional integral. The probability distribution is over the dimension of that space, and you have a local energy at each set of electron positions. And let's take a moment and review how the VMC and DMC energies relate to expectation values of this form and what those distributions are. So in VMC, you're taking the expectation value of the Hamiltonian with respect to some trial wave function written this way. If you write those integrals in real space and rearrange a little bit, you can come to this form with P and identify what P and E are. So P is just this distribution, this normalized distribution f of t, where f of t is the trial wave function squared. So the trial wave function itself serves as the probability distribution. And then you have a local energy, which is described this way, with psi t inverse h psi t. And that's the energy that you integrate over as you vary the electron coordinates. In DMC, it's similar, but a little different. So the expectation value still involves these trial wave functions in the Hamiltonian, but now we have this projection operator, e to the minus th, and we're taking the limit as t goes to infinity. This operator acts on psi t to get a different wave function on the left. This is the fixed node ground state. So once you've taken the limit, you now have this kind of expectation value in DMC, and the integral looks very much the same. You now have this f0 forming a distribution and the same local energy, where f0 is now the product of psi 0 and psi t. For this to really be a probability distribution, you can see that psi 0 and psi t must share the same nodes so that their product is positive, and it can be interpreted as a probability distribution, and that's part of the fixed node approximation. All right, now from these distributions, both of them obey the variational and zero variance principles. So what are those? If you have the Schrodinger equation, we have a ground state solution to it where psi is the exact ground state solution and E is its exact energy, then the variational principle states that the expectation value of the QMC energy will always be greater than or equal to the true ground state energy. And specifically, as the trial wave function approaches the exact wave function by whatever means, the QMC energy approaches the exact ground state energy. The zero variance principle is similar, but it's about the variance. So the variance of the QMC energy is always non-negative. It's greater than or equal to 0 for any trial wave function. But as you take the trial wave function to the exact wave function, the variance pinches to 0. Let's illustrate what that means, the combination of these two means on the right. So on the right, I plot energy distributions drawn from 3 different wave functions. One is, say, the Hartree-Fock trial wave function. The next one is a Slater-Jastrow trial wave function, and finally, the true wave function. And what we see here is that the mean is the expectation value of the energy. The Hartree-Fock energy is higher than the Slater-Jastrow energy and is greater than the true energy. But also the uncertainty in the estimates, and even in the error bar you'll get from QMC with the same number of samples, will be largest for the Hartree-Fock wave function. It has the largest variance in width, whereas if you improve the wave function to a Slater-Jastrow form, you get a narrower distribution of energies. And then as the energy lowers with better and better wave functions, the distribution narrows until it's just essentially one line here, a delta function. And you don't need very many samples to estimate the energy precisely. In fact, if you have the exact wave function, it just takes one sample. So this is just to stress that better trial wave functions simultaneously result in better, meaning lower energies and smaller error bars. Okay. Next, let's take a moment to apply the central limit theorem to understand the scaling of a QMC energy and the energy variance. Okay, it's probably self-evident that the total energy is extensive. This means it scales linearly with system size. So for example, if I have a collection of atoms in a gas that aren't interacting with each other, then the total energy of the gas is just the sum of the energies of the atoms. Okay, that's pretty self-evident. But how does the energy variance scale with system size? That's a little less evident, but we'll go through that now. The applications of this are, one, a transferable wave function quality metric, which is the variance to energy ratio, and second, the ability to predict sampling needs for larger systems from smaller ones, because you can predict how the variance and hence the error bar will scale as you go to larger systems, larger collections of molecules, or larger supercells of a solid relative to smaller ones. Okay, and we'll get there by considering this gas of atoms, where each atom has its own energy distribution, call it P atom of E, and imagine I sample random variables from each of these distributions, one random variable sampled from each of the atom's distributions, where each atom has an expectation value of E atom for the mean and a fixed variance of sigma squared E atom. This will be related to whatever the trial wave function of the atom is, and you can construct the trial wave function from the whole system as a product. Okay, so how do we get to the scaling of the variance? Well, we invoke the central limit theorem on the total energy. So the random variable for the total energy is just the sum of the random variables from the atomic energies. And from the central limit theorem, which we reviewed a moment ago, you get n times the average atom energy. That's not surprising. But then you also get that the uncertainty in the distribution follows a Gaussian, which is whose standard deviation is just sigma E atom times the square root of n. And so its standard deviation goes like the square root, and that tells you immediately what the variance does. So as promised, the expectation value of the energy is linear in n. It's extensive relative to the number of atoms, and it's just the atom energy times n. But the variance, which is the square of the standard deviation, is also extensive. It goes linearly in n with the variance of the atom. And this motivates looking at the variance to energy ratio, something that is independent of n, something that is intensive. So the variance to energy ratio of the total is just the variance to energy ratio of the atom. And this forms a transferable quality metric for trial wave functions in QMC, particularly for pseudopotential systems, where if you have, this should always be less than or equal to about 0.04 Hartree for a decent wave function, whereas for a good wave function, it'll be more like 0.02 or 0.01. And you'll have a hard time making a wave function, at least a simple wave function, much better than that. So this is an important quality metric to look at. And it's transferable from atoms ranging from the number of valence electrons from 1 to 20, so from hydrogen to zinc, and basically every atom on the periodic table we've considered so far in pseudopotential systems. Okay, so that's an important quality metric. Now we need to understand how we can account for the sampling, particularly that the samples are not independent, accounting for temporal autocorrelation. So what do I mean by autocorrelation? What I mean is that adjacent Monte Carlo data samples are not statistically independent. And because of this, the error bar is underestimated because there are fewer effective independent samples. All right, so what does it look like? So for uncorrelated samples, these are ones that are independent. If you look at the sequence of values of a random variable x, say you have 256 samples from that distribution. This is just a Gaussian distribution. These are independent. You'll notice it's very jagged. You have more samples toward the middle and less toward the edges, just like you'd expect from a normal Gaussian distribution. And now what does autocorrelated data look like? I show that below. You'll notice by eye that the two are qualitatively different. You have the same number of samples, But what's different here is there's more white space between where it varies up, fluctuates up, and fluctuates down. And if you notice closely, the samples are related to each other. You go up to this peak, they cluster together. You're actually taking very small steps, small changes in between a prior data sample and a following one. And this relates to, this is what I mean by autocorrelation. It's correlated with itself, and there are fewer effective samples. So you can correct the error bar for this by looking at the original error bar, sigma x over m, but instead of using m, you use an effective number of samples, m effective, which you can formally represent as sigma x over square root m divided by some number, kappa, where kappa is the autocorrelation time. So how do you get the autocorrelation time? Let's first review what correlation means. So the linear correlation between two variables x and y is just the inner product of the two time series xi, yi, subtracting their means and divided by their norms. You may be familiar with this. This linear autocorrelation varies between -1 and 1, where 1 indicates perfect correlation. That would mean the two sequences are identical. And 0 means that they are linearly uncorrelated. Okay, but what about autocorrelation? Autocorrelation is just a linear correlation of the time series with itself, but at time-shifted values. So here's the original sequence, and here's the sequence shifted by some number k, where if k equals 0, this would just be the correlation with itself, a 0-time autocorrelation. You'd expect that to be 1, right? And if you take k to be something large, like 200, the correlation between the point at 0 and points 200 away would be uncorrelated. You'd expect this to be 0, but for values of k in between, it will fall between 0 and 1, most likely. And so you can represent that formally as an autocorrelation function, rho of k, where k are the time shifts. And you can plot that here. This is the autocorrelation function, again, at k equals 0. It's purely correlated. It falls in correlation as you look at points further away from where you are until it becomes more or less uncorrelated near 0. And you can define the autocorrelation time. You can obtain that by the integral of the autocorrelation function in this way, estimated from capital K time shifts, because you only have a finite amount of data. K is generally less than m. You don't have to worry too much about these formulae. That will be handled automatically for you in the labs with tools we have on hand, but it's important to understand the concept of autocorrelation as it affects the number of independent samples that you have, and hence accurately obtain the error bar. Okay, where does autocorrelation come from in QMC data? What it really comes from are how the electron coordinates are updated. The electron coordinates are updated generally using what's called the drift diffusion green function, which creates new electron positions from old ones. And the positions are correlated due to the small step that you take with this, that are generated by this Green's function. So you start with a distribution of old electron positions. Formally, you're performing this integral over this Green's function to obtain a distribution of new electron positions, where tau is the imaginary time step. The drift diffusion Green's function itself is a Gaussian, which should be pretty familiar, where you shift by some drift velocity Vd, and the Green's function has a width of square root tau. This is used to generate a random walk, where you take a new electron, a set of electron coordinates is generated from the old one by applying imaginary time step times the drift velocity. That's just a constant depending on where you are, plus a purely random, notice the eta, a random diffusion step with width square root tau. Usually we're taking small time steps, so this is what limits how far you can step from one configuration to the next, and you form a random walk. You'll hear the term walker being used a lot in Monte Carlo parlance, so let me define what that is. A walker is just a set of electron coordinates, and it performs a random walk. It's updated R1 to R2, 3, 4, 5, 6, 7, 8, according to this formula where you see it takes fluctuating steps. It's a Brownian random walk. The size of these steps fluctuates itself, but they're sampled from this distribution, which has which is bounded, has a length scale of square root tau. Now, what does that look like in a real simulation? So here's an image of a real simulation. You can imagine these being, say, hydrogen atoms with one electron circling the atom. And so you have 1, 2, 3, 4, 5, 6 hydrogen atoms with 6 electrons, one circling each one. And I call this a large time step. You can see that each electron takes steps around the atom, this indicated by the length of these straight lines. Whereas if you were to take a smaller time step, a much smaller time step, the electron would move around the hydrogen atom in this way. You'd have this really fine, tiny, squiggly lines. And what you'll notice is that each step is very close to the previous one at small time steps. And that introduces a close relationship between the energy sampled at one point and the energy sampled at the next. As you see, they'll be very similar. And that introduces autocorrelation into the QMC energy data. The autocorrelation will be stronger for small time steps. You'll have fewer independent samples by taking some number of steps than you will if you take that same number of samples with a larger time step. Okay, the final topic I'd like to cover with regard to, that's not the final topic. Next, I'd like to cover the notion of statistical equilibration. This is sometimes referred to as burn-in in the statistics community. You'll also hear it being referred to as warm-up. So what is this and what's it come from? Well, you have to start the random walk somewhere. So you place the electrons basically at some arbitrary place, some arbitrary electron positions. This is chosen by you or by the computer program, and this is not sampled from the equilibrium distribution, but likely corresponds to a low probability configuration of that distribution. And the equilibration period is the number of Monte Carlo steps needed to walk away from that initial point and begin sampling the equilibrium distribution. And I illustrate that here with some variational Monte Carlo and diffusion Monte Carlo data. So here is a trace of variational Monte Carlo energy data. You'll see on the right, it looks like it's sampling well from an equilibrium distribution. Whereas if you look at the far left, this red dot points to the place where it started. And this energy is high, and it's not sampled anywhere by the random walk. It's an unusual point. And it took a few steps to come down and start sampling this. So I denote by this vertical red line roughly where you've equilibrated. For DMC, it's similar. Diffusion Monte Carlo starts by performing a variational Monte Carlo run and then initiating imaginary time projection. When projection begins, as you go forward in time with sampling, you're going to decrease in the energy exponentially toward the equilibrium distribution. And you can see here, I've used a small time step, and so it actually took quite a large number of steps to reach the equilibrium distribution. But once you've reached equilibrium, you'll cut off the rest of this data behind it, and from the data forward, you'll estimate the mean, the autocorrelation, and the error bar. It's important to cut this data out, as you can see if you include it. This bar represents the mean that you would estimate by including it, and it's clearly above the equilibrium mean. So if you don't exclude it, it represents a bias. So we have to cut this data out to remove that bias. Now in diffusion Monte Carlo, I'd just like to pause for a moment to emphasize that there are tricks to reduce the equilibration time. This is with a small time step of say 0.002 inverse Hartree. And you can speed up the equilibration by performing DMC in between with a much larger time step. Say this is larger than you want to use in production, say 0.02. And you can see that the equilibration period, you walk down the exponential much faster with the number of steps. And the point which you begin the small time step DMC is much closer to equilibrium, such that the equilibration time is very short there. And so in the same run with this, in a run of the same length, same overall number of samples, and the same cost, you actually get many more equilibrium samples. And so it's a much more economical way to run things. Okay, now for the final topic in the statistical analysis section, estimating uncertainty in energy differences. This is really important. It has a couple of applications. One, to correctly assign the statistical error bar of energy differences, which appear everywhere in physical and chemical quantities, binding energies, ionization energies, band gaps, cohesive energies, all those things are energy differences. And so this needs to be kept in mind in all those contexts. And two, to assess whether two values actually differ with statistical significance. And this is a different way of thinking about, are two values the same or not? Do they differ? So to illustrate how to do this correctly, consider two Gaussian distributed random variables. So I'll consider these to be means, E1 and E2, with an error bar that fluctuates in a Gaussian fashion, sigma 1e, sigma 2e, represented by these two distributions, E1 in red and E2 in green. So they're kind of similar to each other. You see they have some overlap. The energy difference itself, dE, E1 minus E2, will also be Gaussian distributed, where its mean will be the true difference of means. That's what you're interested in, again, with Gaussian noise. And in this case, the distribution always broadens. The distribution is the square root of the first error bar squared plus the second error bar squared. And you can see that empirically that here in this blue distribution, it's centered around dE, but with a wider distribution, and you have to account for this appropriately. You'll notice here also that this distribution overlaps with 0. So maybe these two energies are similar, maybe they're the same in the end. How do you judge that the difference is statistically significant, that it differs significantly from 0? Well, you compare the average of the energy difference that you get with the error bar. And you can just take the ratio to get n, or in other words, you choose n such that it's the largest value of n you get, such that this inequality is still true. And so the question is, do the energies differ? If what you get is an n that is less than 1, that's less than 1 sigma difference, that means you don't know. There's little evidence that they're different, and you can probably assume that they are the same. If n is 1, that's a 1 sigma difference, and the answer is basically maybe that the energies differ, because there's a 1/3 chance that they're the same. If n is about 2, they probably differ. There's only a 1 in 20 chance that they're the same. And this is the level in QMC that you're probably it's reasonable to assume that you have a difference. But if you want to be really precise, you'd go higher, for example, to n equals 3, and then you're highly confident that they're different. There's less than a 1 in 100 chance that they're the same. For reference, if you are looking at, say, LHC experiments where you want to say if the Higgs boson is real, you don't stop at n equals 1, 2, or 3 for the discovery. You go all the way out to about 5 sigma, because you want to be highly confident that the signal you're seeing is not noise, that it's real. Okay, but this is important in all the work that you'll be doing. Okay, at this point, I'll pause for questions over the statistical analysis portion.
So, Jaron, we've got one question in the chat so far. I apologize if I pronounce this incorrectly, but from Majusa Chu. The question is, what is the meaning of the local energy on the y-axis in the statistical equilibrium slide? So if you go back a couple, why is the energy on the y-axis and what does it mean?
Okay, so the local energy, let me go back here just a second to this slide, actually. So the local energy is psi t inverse h psi t. So you can see that this is a quantity that has units of energy and that it's non-constant. It also depends on position because psi t depends on position. if psi t is exact, right, if it's the true ground state wave function, then H acting on psi will just give you E psi, psi will divide out, and you will get a constant everywhere. So everywhere in electron coordinate space, the local energy will be constant. For wave functions that are not exact, like psi t, this will fluctuate. It will have a distribution of values. And because psi t can become zero, right? So for fermions, it has nodes. This can be very large and it can be very small in a positive or negative sense. And that's what we're plotting here. No, not here, sorry. Plotting here is that the local energy fluctuates. It has a distribution of values, sometimes large and negative, sometimes large and more positive than the mean. But the mean of these values is the expectation value of the energy itself. So you can get there by looking at the VMC energy and the expectation value. If you write this in real space, you factor out psi t squared. That leaves the local energy, where this is now a probability distribution. So the local energy is just a measure of energy that you measure locally at a particular electron coordinate, but it's relative to the trial wave function. I'd like to stress that. Does that answer your question?
The answer is yes, so that's good. They've got a few other questions in the chat. There's a technical one from Guangyang Li, who I'd suggest to post that on the Slack. It's about file names and so on in QMCPAC runs, and we'll address that there after the talk. Then one from Igor Evangelista. How do the Jastrow factors influence the statistics of diffusion Monte Carlo?
Okay, yeah, that's a good question. So I can answer that more or less from here. So you can see here that variational Monte Carlo and diffusion Monte Carlo are related. They use the same local energy, but a different distribution of values sampled. So the different electron coordinates sampled. So in general, the local energy will still fluctuate based on the trial function. And so the fluctuations in the local energy are guided by the trial function. And so like this example on the right, if we were to just use the Hartree-Fock trial wave function, you would have a broad distribution of energies that you're sampling in DMC. And you'd need a lot of samples to get a precise mean. Whereas if you were to use a Slater-Jastrow wave function, the local energy itself will fluctuate less. The variance in the local energy values will be tighter. And in VMC or in DMC, you'll get a tighter distribution of local energies and thus a more precise answer more quickly. Now, formally, diffusion Monte Carlo, the mean does not depend on the Jastrow factor, right? Only on the nodal structure of the wave function. So if you started with a Hartree-Fock wave function versus a Hartree-Fock wave function with a Jastrow, the error, the means would be the same in diffusion Monte Carlo. Okay, these energy distributions here are shown for variational Monte Carlo. In diffusion Monte Carlo, they would have the same energy mean, but they would have different variances. The one with the Jastrow factor having a much smaller variance and thus being much more statistically efficient.
And one additional question from Ravi Ranjan. What is meant by equilibrium sampling?
Okay, equilibrium sampling. From that, what I mean is that you have to reach the high probability region of the distribution that you're sampling. So for example, the variational Monte Carlo energy distribution is different than the diffusion Monte Carlo energy distribution. So you can see that this one has a lower mean, it's centered in a different place, right? So these two distributions aren't the same. I know this had some equilibrium distribution on the right and on the left here, but you have to travel between them. So to become equilibrated is to take steps in the random walk until you reach the high probability region of the DMC, for example, from the high probability region of VMC, because the VMC sample where you begin will actually be a point of low probability for the DMC random walk. So the random walk generally proceeds in the high probability region of that distribution. And that's what I mean by sampling the equilibrium distribution. You start from a low probability configuration and you move to the high probability center.
So there's a few other questions, but I will get to those as the talk proceeds. I do want to interject my own question. So, I mean, these are all important concepts. Can you talk a little bit about how much of this analysis we have to do ourselves and we really need to worry about, and how much is sort of done automatically by tools?
So I would say in general, equilibration, knowing how far you've gone to sample the equilibrium distribution, that's generally done manually by eye. You use a tool to produce a plot like this, and then you more or less estimate yourself where you believe it's equilibrated. And you can choose different equilibration times and judge the sensitivity based on that. But after that, it's more or less from the tools. The tool will compute the mean value, like shown in this horizontal line. It'll compute the standard deviation of the variance. It will compute the autocorrelation time and the error bar for you. So to that extent, the tool does those things. But you do need to be aware of the concepts of autocorrelation time, how the time step will increase or decrease the autocorrelation time, and how to spot whether you have a good error bar or not, for example. So for example, if the run is too short, then the error bar itself is a statistical quantity and fluctuates. If you have too few statistical samples, your error bar itself will be poorly estimated. So that's something you need to be aware of. And you can use the tools to graph these things and assess sensitivity. So there's some of each side. I'd say most of it's automated, but there are some essential concepts that you need to always keep in mind when performing the analysis.
Thanks, Jaron. Yeah, I'd suggest also the first time one does a new system, that's a good time to be extra cautious. How about we continue?
Okay, great. All right. So for the next section, I'll be switching topics now to talk about QMC workflow automation with the Nexus tool. Now, what do I mean by a workflow? What I mean is that there's some process with a goal. For example, you want to compute the diffusion Monte Carlo energy, but there are a number of other steps that you have to perform to get there. For example, you have a molecule and you need to, a molecule or a solid, and you need to relax its structure. You need to feed that structure forward into a DFT calculation to compute the charge density self-consistently. Then maybe you need to do a non-self-consistent calculation to compute the orbitals. Then you need to use QMCpack to optimize a Jastrow factor and finally feed that forward into DMC. This is one example of a QMC workflow. In computational computational electronic structure in general, there are many kinds of workflows that have to be managed in order to produce the desired results. It can be helpful to automate that. Scientific workflow automation tools have grown in frequency and in popularity because they have certain advantages. One advantage they can give is that they can provide the ability to perform high throughput calculations, such as are done by the AFlow or Fireworks tools, like in the materials project. Or they're used because they can simplify the calculation process for productivity. Some of you might be familiar with ASC, the atomistic simulation environment. Both of these are advantages because they allow you to do more in a broader sense or to just be more productive with your time. And I think their growth in popularity indicates the usefulness of this approach. However, existing tools primarily favor DFT codes, especially with an emphasis on VASP. So what about QMC? This is really where Nexus comes in. It was designed to be a workflow automation system specifically with QMC in mind, but with specific goals. One is to make QMC calculations more accessible. to make the learning curve less steep for new users, but also to automate time-consuming steps in the QMC simulation process. And what I mean by time-consuming is your time. It will make it faster for you to get from the beginning of the project to the end. The Nexus tools are hands-off. What I mean by that is there's no longer a need to compose or edit the simulation input files, which by hand, and they differ for each simulation code. So it provides a uniform environment for that. Nexus enables large-scale job submission on a variety of supercomputing platforms. So you can run from laptops and workstations up to the largest supercomputers in a similar fashion. Nexus makes these simulation workflows scriptable. So it uses Python to write scripts similar to PySCF or ASE. And this simplifies and enables things like, for example, scans over DFT functionals, scans over different lattice parameters, scans over, you want to do calculations over a whole collection of molecules, that kinds of things. And also its goal is to support every kind of calculation that is possible with QMCPACK and provide documented examples. I'll note this is still a little aspirational, but the support's very broad to the extent that you can do many production projects all the way through with Nexus, and there are dozens of papers that have been published using Nexus to do calculations of solids and molecules. So I would encourage you to, after these labs, to continue with it on any projects that you want to perform. Okay, core features of Nexus. It provides a Python interface for workflow composition. The Python script that you write basically looks like a meta input file for the execution of all simulation codes. This brings all the simulation programs together in a single coherent framework. So it looks the same and it's easy to work with regardless of the code you're working with. Nexus provides input file generators. So it automatically creates input files based on minimal user inputs. So you can say things in a fairly simple way and it will create a lot of the other inputs that you will need to run the code, but you don't need to specify them all. However, you can specify all the ones that you want. Nexus provides job monitoring. So it automatically executes the simulations themselves, the simulation workflows, and monitors the jobs for completion and passes data between the different simulations, the things that they produce and the things that they need from each other. And finally, Nexus can be used for analysis. You can automatically extract some of the simulation results, and they're all accessible from within the user script. Nexus supports a number of electronic structure codes, such as QMCPACK, PySCF, RMG, the real space multigrid DFT code, Quantum Espresso, Quantum Package, which is a quantum chemistry package, primarily for multi-reference calculations, games, which you probably know, and also VASP. But its primary focus is on QMCPACK. So QMCPACK itself is an efficient and scalable production QMC code. Its focus is on solids, but it's also fully featured for molecular calculations. QMCPACK is geared to work efficiently on parallel computers. So here I show a scaling example where this black line is ideal scaling, and then the boxes and triangles are the actual scaling results on very large computers, Summit and Theta, at Oak Ridge and Argonne National Labs, respectively, with respect to node count. So from 100 to about 4,000 nodes, they have almost ideal scaling. So you can efficiently use any computer that you have access to. QMCPACK gives access to microscopic observables, such as the momentum distribution, which I show here. It also gives access, especially for molecules, to controllable accuracy via advanced wave functions. So for many molecular systems, you can introduce multi-determinantal wave functions from which you can arrive at essentially 100% of the correlation energy from QMC directly. And these are more efficient than CI methods alone. You will reach the correlation energy limit with many fewer determinants. And so this can be very useful for benchmark quantum chemistry calculations versus other methods. For example, QMC-PAC also can perform calculations of solids, especially many applications have been made to correlated materials, and more recently now toward quantum materials, where spin orbit's important. And QMC-PAC is supported by the Center for Predictive Simulation of Functional Materials, as well as the Exascale Computing Project. Okay, back to Nexus though. Nexus supports the execution on a range of machine environments, all the way from workstations to intermediate size institutional clusters, all the way up to leadership computing environments such as Summit at Oak Ridge. And in QMC, this is useful because different parts of the workflow have different costs. For example, DFT is cheapest and DMC is more expensive. So you might be able to run the DFT or the Hartree-Fock or the quantum chemistry run on a workstation and perform data analysis there, but you'll likely need to move to a parallel cluster of some kind to perform the wave function optimization in DMC, for example. And so an institutional cluster could be used to do production DMC of small to medium systems, and probably VMC and optimization of even pretty large systems. But for the larger systems, you might need a leadership computing environment for diffusion Monte Carlo. And by that, I mean a system with, say, a couple hundred atoms. You'd need a very large computer to run effectively. But all of these are supported by Nexus because your calculation needs span these different environments. Okay, just to note, Nexus has built-in support for known machines at several supercomputing centers, for systems at Oak Ridge National Laboratory, the Oak Ridge Leadership Computing Facility, Andes and Summit, the Argonne Leadership Computing Facility, computers at Sandia National Lab, NERSC, which some of you may have access to. It natively runs on Cori, and also at the NCSA at Illinois and the TAC in Texas, as well as other centers. And I'd like to emphasize that adding new machines, your own institutional cluster or another computer you have access to, is easy. It only takes about 40 lines of Python code, and I encourage you to reach out to the developers, including myself, if this is something that you'd like to do, because it won't take too long to do so. Okay, I'd like to just illustrate an example of Nexus workflow execution. This is a workflow more like what you'll be doing in the labs today. For example, this straight through workflow is a lot like what you'd do if you wanted to compute the DMC energy of, say, coronene, the molecule coronene, or the material diamond. You'd start with a DFT calculation using, say, PySCF for coronene, or maybe Quantum Espresso for diamond. That DFT calculation would produce the orbitals for the Slater determinants. And next, you'd convert the files coming out using, say, Convert for QMC or PW-QMC-PAC. These are QMC-PAC executables, but they'll convert the orbitals into a file format that QMC-PAC can use. Next, you'd perform Jastrow optimization with QMC-PAC, and finally, diffusion Monte Carlo with QMC-PAC. So Nexus runs all of these calculations, but it also processes the dependencies between the calculations. So it supplies information from one simulation to the next, depending on its needs, and will run them in sequence. Also note that Nexus can manage many of these workflows simultaneously. So if you have workflows like this or more complicated, but you're doing them for 100 molecules or something, you can manage them all at the same time on your computing cluster all at once. Okay, so what does it look like to work with Nexus? Today we're going to be using Nexus pre-installed on the virtual machine, but I'd like to show you that it's easy to do so on your own laptop or cluster. All you really need is Python. So to download, you just make a path, call git clone on the QMC-PAC repo like this, and go in it after you download. Installation is just adding 2 lines to your bashrc file or at the command line. you export your path to Nexus lib, and your Python path, sorry, and export your path to Nexus bin. This enables Nexus generally, and this enables Nexus executables. So once you've done those two things, Nexus should work on your system as long as you have Python and NumPy installed. And you can check that your install works by running the Nexus test executable. That should already be in your path after this step. And in about a minute or so, it will run through all the tests, and it should tell you that the Nexus works on your machine. Okay, what does Nexus look like to work with from a user perspective? So I mentioned this user script. So this is what an actual user script looks like to specify a workflow. First, you have the generic Python interpreter for any Python script. You import some key functions from Nexus, and I'll go through what those functions are just now. The first is the settings function. These are your user settings. You point to, say, for example, where your collection of pseudopotentials are. You tell it what kind of machine you're on, in this case, a workstation with 16 cores, so it knows what resources to utilize. And this sleep is a polling frequency. So it will poll, it will check on the simulations it's running every 3 seconds for completion and execute new ones if the old ones have finished. On a cluster or a supercomputing center, you might want to increase this to, say, every 5 minutes or every 20 minutes, because Nexus will sleep in between using no resources and just occasionally wake up and check on what it needs to do. Okay, next, you define the physical system you're working on. This will be shared for all the simulations following. So for example, I want to run a supercell of diamond. I give it the primitive cell axes. I say there are 2 carbon atoms in the cell at these positions. And then you can automatically tile it, so multiply it by 2 in each direction to obtain a 16 atom cell. This looks a little bit complicated for things like molecules, and even for solids. You can just, as you'll see in the labs, you can just provide a path to a structure file, like an XYZ file, and it will read it in. Okay, next is the workflow composition part. And here I show a 3-step workflow. So just starting with PWSCF, Quantum Espresso, to do an LDA calculation of diamond. You'll notice you don't have to say very much to specify what you want to do. Next, an orbital conversion step with PWQMCPack. And now you'll see there's this dependencies line. This says that this calculation needs to execute after this one, and it should extract orbital information from it. Finally, just running VMC with that Slater determinant with the converted orbitals coming from PWQMCPack. This composes the workflow. And then finally, once you reach this run project function, this is when all the workflows will be executed, when Nexus will begin to execute and monitor these simulations. Okay, now what's it look like to use Nexus from the command line? So that was basically writing your input file a moment ago, and now you need to execute everything. What does that look like? So one thing you can do is you can graph the workflows that you've composed to check how they look. For example, if I did that on the example above, this image would be shown, showing the 3-step workflow. You can check on the initial status of all the calculations. Of course, nothing's been done yet, so it will show you where each simulation will be run, what path it will execute at. And these are status flags, nothing's been done yet. And then you run the script without any flags, and it will begin executing. And so at time 0, it starts out, it creates this directory for the DFT. It will go inside and execute pw.x. It will generate this input file and execute this. And then every 3 seconds it monitors until the simulation completes, at which point it will start the wave function conversion step, generate the input file and run PW2QMCPack, monitor and complete, and then finally generate the VMC input file, run QMCPack, and monitor and complete it. Once that's all done, you'll see this project finished part, and you can check the status. You'll see that these status flags are all set to 1. In the labs, we'll explain more about what those mean. But you can see all the runs are completed, and it stores the the local process ID or the submission number ID on the cluster that you're on as a record. And finally, you can process any results. In this case, I'm just using grep to look at the DFT, the LDA energy, or the QMCA tool, which we'll cover later, to extract statistical quantities from the QMC data. All right. So today we're working with Nexus just on the virtual machine, basically on laptop or workstation environments, but I wanted to show that the changes you need to make to the user script are pretty minimal, going from a workstation type environment to institutional clusters or even leadership computing environments. So on a workstation, in settings, you set the machine to be some kind of a workstation. And the jobs, these are the simulation jobs you provide to each simulation, specify, say, the number of cores and the threads you want to use. So 16 cores, 4 threads, that will generate an invocation like this, where it sets the number of OpenMP threads to 4 and the number of MPI processes to 4. So 4 times 4 is 16. It'll populate all the cores. Now, if you're on an institutional cluster like CAIDS at Oak Ridge, you instead tell it that you're on CAIDS. The machine is CAIDS, and usually you'll have some type of an account for the hours, the computing hours you have access to. So you set the account. Our account name here is just QMC. And then all that's different below is how the job is specified. Instead, you just ask for a number of nodes, how many threads you want to use, and how long you want to run for. And instead of this type of command line execution, Nexus will generate a job submission script appropriate to the machine and then submit the job. And similarly for an even larger machine, if you want to run on a leadership style, say on 1,000 nodes at Theta at ALCF, it looks very similar in Nexus, but very different in what type of submission script is automatically generated. But I just wanted to stress that this is very similar for these different machines. And so you can start out by, you can warm up to using Nexus on workstations and then very easily extend to larger machines from there. Okay, for more information on Nexus and QMC Pack, I'd refer you to the general documentation for them. QMC Pack's documentation is at this link. And the page is shown here. And for Nexus, it's at this link. This has many more examples and much more in-depth explanation of these codes and how to use them. I'll post any links shown in this talk in the Slack afterwards so that you have easier access. But also note these slides are on GitHub, so please also you can download the slides from the workshop GitHub page and access the links directly that way. Okay, any questions about Nexus?
So we've had a lot of questions about trial wave functions and general questions about workflows. None yet about Nexus that haven't been addressed. Let's just give it a minute to allow people to type.
Okay, I mean, workflow questions are also appropriate.
I'll just scroll to make sure I haven't missed one. Actually, I'll echo a question here that I attempted to address earlier that was asked by Igor Evangelista. And he writes, I know that DMC calculations are computationally expensive and Nexus is an automated tool. How can I make sure that my initial data, so DFT plus VMC, is correct and Nexus should proceed with DMC calculations?
Okay, so often a good intermediate step is to run a VMC calculation, right? Because it's much cheaper. And you'll catch any problems with the wave function, the trial wave function, which of course, part of which is generated from your DFT calculation there. So I'd perform a shorter VMC calculation first with Nexus on whatever resources you have, and then go and inspect manually with, say, the QMCA tool, the results of the VMC calculation. And what you'd want to look for in terms of quality are, for example, the variance and the variance to energy ratio. You will often spot problems with the orbitals or with the representation of the orbitals there. So for example, in periodic calculations, orbitals are represented on a 3D mesh of B-splines, and in molecular calculations, of course, they're represented in a linear combination of atomic orbitals. But you want to make sure that it looks good at the QMC level, and that will show up on, say, the variance to energy ratio in QMC-PAC. For just a bare Slater determinant wave function that comes directly from DFT, the variance to energy ratio will likely be about 0.2 or 0.15 Hartree. If it's much larger than that, there's probably already a problem with your orbitals. If you proceed, but to get a better read on the wave function quality, you should optimize a Jastrow factor and then look at the variance to energy ratio. If that's larger than about 0.04 Hartree, then there's some issue that you should address first with the trial wave function, and then come back, either optimize it more, fix issues with the orbitals, that kind of thing. And then add the DMC section to your Nexus script and run. I'll just note that Nexus scripts can be added to over time. You can add new blocks to them. If you rerun the script, Nexus will not run the pieces it's already run, and simply add the new pieces and run them. So you can continually add things to it over time as you explore things yourself over time.
Thanks, Jaron. We're getting a couple of questions about some possible issues in the virtual machine, which we'll address after this these presentations and over the coming days as needed. And I see time is moving on, so let me just ask one more of the questions here. And this is from Daniel. Does Nexus include error handling with some automated scenarios, convergent checks, etc.? Or is error handling done by hand, stroke other tools?
So there's a mix. Nexus cannot capture every possible way a code running underneath it can fail. So those ways are extremely diverse. But it does try and catch as many errors as it can. So for example, it will notice whether the DFT run has completed successfully or not. It will observe, say, the variance to energy ratio of the Jastrow optimization, and it will refuse to perform the subsequent steps in the workflow if it can catch an error that way. What you'll see as a user is, for example, on this, after you've run part of it, you can interrupt the workflow at any time and reinitiate it. But in between, you can run the status check and look explicitly at the status of the different runs. If Nexus has detected an error, it will show up as a 1 in this column instead of a 0. And then you can go look at the run. So Nexus can't know all of what's happened in the run, but hopefully you, as an experienced user, can. You can go look at the run, see what's wrong, adjust inputs, and rerun. With Nexus, you can simply back up the files in that local directory to somewhere else, and then rerun the script with adjusted inputs, and it will rerun things starting from there.
Great. Do you want to move on at this point?
Yeah, I think next is just a break for a few minutes. Okay. For our final topic today, we'll be covering the hands-on section of the workshop. This is going to be the first set of lab examples that you'll get to do with the virtual machine. Today we'll be covering basic variational Monte Carlo, Jastrow optimization, and diffusion Monte Carlo on the virtual machine, where you'll get to practice both running quantum Monte Carlo calculations with QMC-PAC and Nexus, but also to practice and develop the statistical analysis skills that we've gone over in today's lecture. Okay, so to access the lab material, go to this link online. You'll notice this first part's just the QMC workshop link. You can go directly there and then just navigate through the folder structure that you can see in the browser to week 3, Stats and Nexus. I'll leave this up here for a moment in case someone is really ambitious and wants to type this in. However, I recommend again that you just download the slides or look at the Slack channel afterwards for this link that I will post.
I posted it in the Slack, in the chat.
Thank you, Paul. Okay, and if you go to that link, what you'll see is this page. These directories contain the lab examples, but what you'll notice in a browser is that automatically this README will show and render. And this is the README for the lab overall. I'd recommend that you open a browser and follow the README through for the lab directly there. And in a separate window, open the workshop virtual machine and run the examples. In each subdirectory, in each example of the lab, there's also a README file there. So first read through the top level README and then click through to each example and follow the README in each subdirectory as you work through the example on the virtual machine. Just to remind on how to use the virtual machine, first open up VirtualBox, select the image you want to load and push start. That should start up a virtual Ubuntu session. And from within Ubuntu, click on the terminal application icon, and that should start you up in a terminal. Once you're in the terminal, there's an important step that you need to take, and that is to update the workshop example files. So navigate from the home directory into the QMC workshop directory and perform get pull at the command line. This will load all the updated lab materials as well as today's slides into that local directory. And from that point, you'll be ready to start the lab. Then navigate into week 3 stats and nexus, and you'll be able to navigate into each subdirectory from there and proceed the laboratory as you follow the READMEs in the browser. Okay, before I get into what the lab examples themselves are, I would like to take a moment to introduce the QMCA statistical analysis tool. This is the main tool that you will use interacting with QMCPAC to analyze the data coming out of it. In a QMCPAC run, many files are produced, but the one to focus on are the ones with a .scalar.dat at the end of them. These contain the traces of scalar statistical quantities. Scalars meaning single numbers, like the energy, the kinetic energy, the electron-electron energy, that type of thing. But the QMCA tool is used to analyze the time series data coming from them. So here's an example of how to make a trace plot of QMCA. Say QMCA-T, that's for trace plot. -Q, quantity, E, that's the local energy. -E0 means no equilibration time, and then pointed at the file. It should produce a plot that looks like this. So you'll see the time series of the local energy data, and this dashed line represents the equilibration period that you've provided, here in this case 0. So it's not excluding any of the data. To remove the equilibration period, just provide a finite number via -E. In this case, I provided -E 100. That should move this vertical dash bar to 100 if you provide the -T flag to make the plot. But whether or not you make the plot, it will now compute a mean energy and show you the error bar. So it'll produce this line. It will tell you that the mean of the local energy is this, -45,877 Hartree. And the error bar, the 1 sigma error bar, is ±0.017 Hartree. And again, this is including autocorrelation, the degree to which it can estimate it. And how you show the autocorrelation time is you add a --SAC flag. And you'll notice that the mean and the error bar are the same, but on the right, it will show you what it estimated for kappa, the autocorrelation time, in this case, about 5. So about 5 of these samples next to each other were autocorrelated, and it had to account for that in the number of effective samples and increase the error bar. What I'll note is that for good statistics, you want the number of effective samples to be greater than about 100. That's a rule of thumb. So you can see I've got 800 samples or so, or actually 700 after I've cut off 100 of them And if you divide by 5, that's a number larger than 100. So it has a more than 100 statistically independent statistical samples. Okay, why is that useful? Well, it's important for estimating the error bar well. The error bar, as I said, is a statistical quantity itself. It depends on the estimated variance. And if you have too few independent samples, the error bar itself will be noisy. So if you ran many independent runs and computed the error bar, this number would fluctuate. You get large and small error bars. But if you have more than 100 independent samples, you'll have a good estimate of this error bar. It will be consistent and meaningful for your subsequent analysis. Okay, finally, with QMCA, an important quantities to be able to analyze, in addition to the energy, is the variance and the variance to energy ratio. You access those by saying -QEV. That will give you the energy and the variance at the same time. And for example, now I'm pointing it at a collection of scalar.dat files from the different iterations of the linear method during optimization. And so I've only shown 2 lines here, but there will be many more. And in this case, it now shows not only the local energy and its error bar, but the variance and its error bar. This is in Hartree squared, and then the variance to energy ratio in Hartree. And again, like I said, when the optimization begins, you don't have a Jastrow factor. The variance to energy ratio is about 0.16. That's about the expected number. And then as you have a more optimized Jastrow, it falls below 0.04. In this case, representing a pretty good wave function. Okay, for full documentation with more examples about QMCA and how to use it, you can go to this link in the QMC Pack documentation. This is right in the QMC Pack manual. It's just one section on QMCA. And I encourage you to skim it at least. Okay, now for the lab examples themselves. Okay, for the first example, we'll be looking at the diamond equation of state using the Quantum Espresso code. This is in the directory diamond EOS workflow. It's the first example. And the goals here are to compute the energy versus volume curve at 7 different lattice constants of diamond and fit the equation of state to find the equilibrium lattice constant. The main goal here is just to gain familiarity with Nexus and to learn the major functions in the user script. So it's an extended example that explains Nexus as you do it. So running the example, you just run the diamond EOS script. And as example results, here you can just grep from the output files the energies. And if with an editor, you put them in a data.txt file, you can use this locally provided Python tool to perform this fit, and it should show a graph like this, and estimate the equilibrium lattice constant. So I'll emphasize, I'm just showing a single slide about the lab. There's a lot more material in the README in the lab itself. So I'd encourage you to walk through the README and perform the lab, not just from this slide. Okay, next, the next 3 examples are all now running workflows for quantum Monte Carlo. And they're all use a single molecule as their base example. So we're going to be looking at the lithium hydride molecule. We're using pseudopotentials here, so it's actually very simple. There's just 1 electron around hydrogen and lithium each in a singlet state. So it's a 2-electron example. And in this first QMC example, this example 2, we'll be calculating the Hartree-Fock energy with PySCF and also with QMC Pack by using the Slater determinant wave function. The directory is LIH HF VMC, and the statistics in QMC topics, which you'll be going over through this lab, are to estimate the VMC equilibration time, estimate the VMC energy mean, variance, and error bar, estimating the autocorrelation time properly, and obtaining more precise estimates through using your understanding of the central limit theorem. This example's run like the others. You just run the script directly. And as example results, you can extract the Hartree-Fock energy from the PySCF run and use QMCA to compute the local energy and its variance of the Hartree-Fock Slater determinant wave function. And you'll see you get a number very much like what PySCF produces, It's not numerically the same because you have a statistical error bar, and you can see the local energy trace here. Okay, in subsequent examples, we'll get a little more advanced. And in example 3, you'll look at optimizing Jastrow factors with QMC pack for lithium hydride. Here, well, the directory is LIH opt VMC, and the topics of note are the two-body Jastrow factor form, performing Jastrow optimization with the linear method, judging the quality of the wave function optimization performed, getting more familiar with the utility of the variance to energy ratio, and using your knowledge of the statistical significance of energy differences to assess the convergence of the optimization process. You run the example as before, and here as an example of the results, we use QMCA on the collection of scalar files. Each scalar file corresponds to one iteration of the linear method. We produce a whole sequence of energy means, variances, and ratios. And probably most usefully, you can also use QMCA to produce plots with respect to iteration count of how the local energy progresses as the parameters of the wave function are updated. You can see the local energy decreases and more or less flatlines, and so does the variance. Okay, as a final example, you'll be looking at diffusion Monte Carlo calculations of the lithium hydride molecule from a few different angles. The directory is LIH-DMC. The topics of note for this example are the exponential properties of the DMC equilibration. I'll note this actually isn't a wonderful example for that because LIH is such a simple system that the Jastrow factor accounts for much of the properties of the wave function. And so with the statistics we can access, you don't actually see much of the exponential period, but you'll go through analyzing it anyway for this example because it's an important topic, and examples in later weeks, you should be able to see this more directly. We'll also look at the effects of the longer autocorrelation time in DMC, which is inbuilt to DMC due to a necessarily smaller time step. The smaller time step and the resulting autocorrelation time in DMC is exactly what makes DMC more expensive than variational Monte Carlo because it takes more steps to produce uncorrelated samples. We'll look at DMC time step extrapolation. A finite time step is an approximation in DMC, and taking the 0 time step limit, you'll arrive at the theoretically correct DMC energy. For total energy differences, finite time steps produce very good results in the energy difference. And if you look at the energy difference as a function of time step, it will be flat, likely for all values lower than about 0.01 inverse Hartree. We'll finally look at DMC population control bias. DMC uses a whole collection of walkers all tied together in a branching process, and this has important consequences. Again, LIH is a little simple for this, but we'll learn about it in this context anyway because the example runs very fast on your laptop or workstation. And finally, you'll learn a little bit more about the statistics of resampled curve fits through the time step extrapolation process. You run the workflow as before in a very similar fashion. I'll just show some example results from the time step extrapolation portion. Here, we're looking at 3 time steps, larger, smaller, and smallest. And you'll see that the local energy changes as a function of the time step used. You'll use the QMC fit tool distributed with QMC pack and nexus to perform an extrapolation of the DMC energies as a function of time step to the 0 time limit. Internally, it uses a resampling algorithm, in other words, performing the fit many times as these statistics are varied to produce an intercept at 0 time with its own error bar. I'll note here that DMC is expensive, and so these runs will take a few minutes, hopefully not more than 10 minutes, whereas all the other examples will take more like 30 seconds on your laptop. Okay, finally, are there questions on the lab material?
So, Jaron, I don't see any in the chat currently. Let's give people a minute or so to type. And did you cover updating the workshop files in the image? Maybe that might be worth restating.
Yeah, we can dwell on that for a moment. So once you have a terminal up and running on your VirtualBox machine, again, just cd into the QMC workshop directory and execute get poll to update all the README and input files for the examples to their current versions, current and final versions for the lab.
So I don't see any new questions, but I'll echo one we didn't answer actually from earlier, and this is from Edgar Lantinez-Border. Can I customize JASTRO function selection within the Nexus workflow?
Yes, you can. There aren't a lot of documented examples of that. Nexus does automatically select the what it believes to be the most appropriate JASTRO factor, but there are ways to specify which one you wanted to take by hand. So again, for those who are in the audience, the optimization process executes over several iterations, and at each iteration, it will produce a trial wave function, a trial JASTRO with different parameters at each step of the optimization process. And you can take any one of these as a trial JASTRO to feed forward into a subsequent VMC or DMC calculation. So Edgar's asking about how Nexus selects the best JASTRO factor to use in the next simulation and whether you can have more control over which one it picks. So again, the answer is yes, you can tell it which one specifically to use or change the criteria it uses to perform the selection. But this is more of an advanced topic, so I would say post more about this in the Slack or via email on the QMC Pack GitHub page, and we can more fully answer how to perform that specific selection. All
right, Edgar says thank you. And I don't see any other questions yet, so perhaps you can wrap up.
Okay, so to wrap up, in summary, we've covered, I've covered three major topics here for today. One is a proper statistical analysis, including statistical significance, accounting for the equilibration and autocorrelation effects, and applying the central limit theorem, as these are essential for QMC practitioners in analyzing the meaning of the results. Noted that QMC calculations are actually workflows of interconnected simulations, and that these can be managed efficiently with the Nexus workflow tool. Finally, we've gone over the lab examples so that you can gain more practice in your statistics skills in the context of real VMC, wave function optimization, and DMC calculations with QMC Pack. Again, please tune in next week for molecular QMC calculations being presented in more detail by Anwar Benali from Argonne National Lab. And there you'll get to gain experience with both single and multi-reference wave functions for molecules in the workshop virtual machine. We have a little bit of extra time today, and so I'd encourage everyone to use the time that we've not taken up in the lecture today to start out in the labs, get your feet wet and your hands dirty, and ask any questions you have on the Slack. I will be available over the next couple of hours dedicated for the labs, and also interspersed throughout the week. If you have questions with the labs, please work on the labs and post any questions you have to the Slack. Thank you very much.